Welcome to Kautilya. The previous class I discussed about earth rotation and earth revolution, and I have seen the results of earth rotation like the formation of day and night, deflection in the direction of winds, deflection in the direction of ocean currents. Then in earth revolution we have seen the effects of earth revolution as the occurrence of seasons and variation in the lengths of days and nights. So apart from this occurrence of seasons and variation in the lengths of days and nights, the other results of earth rotation are aphelion and perihelion. So this aphelion and perihelion is due to the rotation, the revolution of the earth around the sun. Here aphelion and perihelion means when this earth is revolving around the sun throughout the year, the earth is revolving around the sun throughout the year. Now this earth at one time it comes very close to the sun, and at another time it moves farthest from the sun. This position, when earth is very close to the sun, not only sun, any object in the solar system, when it comes very close to the sun, then it is called perihelion. Whenever the earth moves farthest from the sun, it is called aphelion. So look at this picture here. Here this is the sun, location of the sun, and it is the position of the earth. Now at this time see, this earth is close to the sun, so it is called perihelion, and earth is farthest from the sun, it is called aphelion. So all the elements or all the objects in the solar system follows this aphelion and perihelion, but when earth is close to the sun, it is called perihelion. Remember, and it is the question which had been asked in 2008 group 1. In that year the question was, when earth comes very close to the sun, it is called as A, aphelion, B, perihelion, C, apogee, D, perigee. So that means it is, the right answer is aphelion here, perihelion here. Now in the case of the earth, for example, any body, if it comes very close to the earth, for example today the moon which is revolving around this earth, when this moon comes very close to the earth at a particular time period, so if it is the position of the moon and if it is the position of the moon, now this time moon is very close to the earth, then it is called perigee. And when the moon is farthest from the earth, it is called apogee. So not only this moon, any satellite launching from that surface, today we know that there are different satellites which are launching from earth to the space. For example, if a satellite is moving around this earth, and when the satellite comes very close to the earth, then it is called apogee of the perigee of the satellite. It is perigee of the satellite. That means it is closest position of that satellite to the earth. When the satellite comes very farthest to the earth, then it is called apogee. It is the farthest position of this particular satellite to the earth. So that means apogee, perigee with respect to the earth, and perihelion and aphelion is with respect to the sun. Okay. Now in general the perihelion and aphelion occurs on these days. So on these days, in this case, see, on the days of perihelion there will be shortest distance between the sun and the earth, and it is 147 million kilometers. At the time of aphelion there will be maximum distance between the sun and the earth, it is aphelion. So this aphelion occurs around July 3rd. Aphelion occurs around July 3rd, whereas perihelion occurs around January 4th every year. Perihelion occurs around January 4th and perihelion occurs around July 3rd. That is how on this day there is maximum distance between the sun and the earth, and in this day there is shortest distance between the sun and the earth. In that way, the average distance between the sun and the earth, is around 149.5 million kilometers, or it is 150 million kilometers. and this distance of 150 million kilometers in astronomy, remember, it is called as 1 astronomical unit. So this distance of 150 million kilometers in astronomy is called as 1 astronomical unit, and it is also the question asked in the previous exam. One astronomical unit is A, distance between the sun and the earth, B, distance between the earth and the moon, C, distance between the moon and the sun, D, distance between the moon and Mars and the Jupiter, like that. So it is the distance between the earth and the sun. It is 1 astronomical unit. It is a unit to measure the distance, right? Then one more effect of the earth revolution is eclipses. So eclipse means, in general, eclipse means a shadow. Eclipse means a shadow. So these eclipses occurs on a particular condition when the position of the sun, moon and earth are on the same line. That means when moon, sun and the earth becomes collinear, when these three objects becomes collinear, at that time there is occurrence of these eclipses. Means in the case of eclipse, when the sun rays are coming, these sun rays are incident on one object, either on the earth. Now here there will be shadow because this part of the earth getting the light, but another part of the earth do not get the light. So now here this moon comes into a shadow formed by this earth, and that is how when moon comes into a shadow formed by the earth, it is called as lunar eclipse. Lunar eclipse. But in other case, when sun is here and it is the light radiated from the sun, and if it is moon's position here, and here there is a shadow formed by the moon, and if it is the earth, here, now this some portion of the earth comes into a shadow, some portion of the earth comes into a shadow formed by the sun, then it is called solar eclipse, because on this day these people on the earth surface, they cannot see the sun. It is called solar eclipse. So that is how eclipses are of two types, and these eclipses occurs when the sun, the moon and the earth comes onto the same straight line. When the sun and the earth and the moon are comes onto the straight line, then these eclipses occurs. This is also the collinearity of this. But there are two types of, generally these eclipses are of two types. One is total solar eclipse. Total solar eclipse or total lunar eclipse, or otherwise there will be total lunar partial solar eclipse, and partial lunar eclipse. So this partial solar eclipse and partial lunar eclipse occurs frequently, whereas total solar eclipse and total lunar eclipse occurs very rarely. For suppose, the difference between partial solar eclipse or partial eclipses and total eclipses is like this. So partial eclipse means when the position of the sun, moon and the earth on the same straight line, even though their plane is not same. That means the plane is not the same, but the sun, moon and the earth are seems to be on the same straight line, then it is called partial eclipse. But when the sun, this moon and earth on the same straight line, number one condition. Number two, if they are coplanar, means if they are lies on the same plane, if they are lies on the same plane, then it is called total solar eclipse or total lunar eclipse. It is the condition for total eclipse. So, but in general, in a month you will get two partial lunar eclipses or in a month you will get one partial lunar eclipse and one partial solar eclipse. Okay. Now first let me explain you again the total the solar eclipse. You can see in the picture, it is a picture which explains us the solar eclipse. Now in this picture you can see it is the sun. Now it is the light coming from the sun. It is incident on this moon. Now this moon obstructing the light not to fall on this earth surface. That's why this particular portion of the earth, is under shadow formed by the moon. So that means this particular portion of the earth is under shadow, and which is called lunar eclipse, solar eclipse, because these people on this earth surface, they cannot see the sun, because here there is obstruction caused by the moon. Now here the complete shadow region in between the moon and the earth is called umbra region, and here the partial darkness is called penumbra. Okay. So in the case of total eclipse, here there will be the complete shadow is here, very limited portion of the earth is under shadow, but in the case of partial eclipse there will be more major portion of the earth is under shadow. That means in the case of partial solar eclipse there will be no coplanarity of between the plane of the earth, plane of the moon and plane of the sun, but in the case of the total solar eclipse there will be coplanarity between the among the sun and the moon and the earth. Now in the case of total solar eclipse, you can see in the case of total solar eclipse, the person on this earth surface, he can see only this outermost part of the sun, and you know the outermost part of the sun is called corona, and on this particular day this corona of the sun appears as a brightening diamond, or it appears as a diamond ring. So on the day of this total solar eclipse, this structure of the sun is called diamond ring structure. Remember, diamond ring structure means on this day this person on this earth surface, he cannot see the surface, the photosphere of the sun, but he can see the outermost part of the sun, only this portion. So that is called corona, and this corona appears like a diamond ring, so it is called diamond ring structure of the sun. That's enough. Now in general, on the day of solar eclipse, whether it is partial solar eclipse or total solar eclipse, this day what happens, when half of the moon is getting the light, here this portion of the moon is getting the light, but the remaining half is not getting the light, so this part of the moon is under darkness. So that means these people on that surface, they cannot see or they cannot observe the presence of the moon in the solar system. So the presence of the moon in the solar system or in the space cannot be observed on this day of the total or partial solar eclipse. That's why this solar eclipse results as a new moon day, or in Telugu Amavasya. So on this day you cannot see the presence of the moon in the sky, so it is called new moon day or Amavasya. Clear? But in the case of the lunar eclipse, see, look at the picture here, it is lunar eclipse, means when the sun is here and it is the earth which comes in between the moon and the sun, and it is the position of the moon. Now this day these sun rays are directly incident on this earth, that means this portion of the earth is getting the light, other half of the earth is in darkness, and the moon comes into the complete shadow formed by the moon. So that means here sun, the earth and the moon are in a line. Here the earth casts a shadow across the moon as its orbit into the sun's earth. Now the moon will darken and may become red like smog or a sunset, or illuminated with a light scattered by the earth's atmosphere. Means here this day, even though there is no direct incident of the light on the moon, but this moon gets illuminated due to the light scattered, I mean the light reflected from that surface, will incident on the moon surface, other area of the moon surface. This day, in this manner, even though the remaining part of the moon cannot be observed, this portion cannot be observed, but this portion which is illuminated by the reflected light of the earth, the light which is incident on the surface, it gets reflected, and due to that reflected light, the illuminated portion of the moon, the moon gets illuminated. So that means you can see the maximum surface area on this particular day. You can see the maximum surface of the moon on this particular day. So as we can able to see the maximum surface of the moon on this particular day, so it is called full moon day. Full moon day, or in Telugu it is Purnima. So that is how this day of total solar eclipse results as this day of lunar eclipse results as full moon day, or if it is partial lunar eclipse or total lunar eclipse, ultimately it results as a full moon day or Purnima. Remember, right? So that is what happened in the case of lunar eclipse and solar eclipse. So with that, the results of the earth revolution are over. Now in the sum up, I'll tell you something about this earth revolution. So earth revolution, finally the effects of the earth revolution are: number 1, seasons; number 2, variation in the lengths of days and nights, lengths of days and nights; and number 3, eclipses; and number 4, aphelion and perihelion. And of all these things, seasons is the most important one. So these seasons occurring on this surface due to earth axis, or so this due to this inclination of the earth with respect to the sun. This is this inclination I told you, 23.5 degrees inclination, or it is called tilt of the earth. Tilt of the earth, we are getting these seasons. And I also mentioned you, it is all due to the relative position or the relative movement of the sun with respect to the earth. So it is equator, it is Tropic of Cancer, and it is Tropic of Capricorn, and this sun moves from Tropic of Capricorn from December 22nd to equator by March 21st, and this northward migration of the sun further towards the Tropic of Cancer by June 21st. Again, this moon will coming back to equator by September 23rd, and he will again coming back to the Tropic of Cancer by December 22nd. This is how in a time period of 1 year, the sun moves towards north and as well as coming towards south. So that is how we can say the northward migration of the sun. Northward migration of the sun is from December 22nd to June 21st. December 22nd to June 21st. Whereas the southward migration of the sun is southward migration of the sun is from June 21st to December 22nd. So remember these points, right? So with that, the effect of earth revolution is over. Then we'll move to the next topic, next important topic, and it is actually, up to now we discussed about the basic details of the evolution of the earth, from the evolution of the universe and evolution of the solar system, and the details of the planets in the solar system. Then we have seen earth as a planet, and there we discussed about the globe, which is a paradigm, it's a model to discuss about this earth. Then we have discussed about the effects of the earth rotation and earth revolution. With that, the basic introduction to the geography is over. Then we are moving to the next most important topic, or which is a new topic or new chapter. You can say it as geomorphology. Geomorphology, or it is the study of landforms. Study of landforms. Today on this planet Earth, there are different types of landforms. These landforms are developed on the Earth's surface by different mechanisms, different processes. So these mechanisms or these processes which led to the formation of these landforms on the Earth's surface. So the study of the evolution of these landforms and the types of these landforms and the distribution of the landforms is nothing but geomorphology, which is the first chapter of physical geography or world physical geography. Now, the landforms on the Earth's surface can be broadly divided into three categories. So the landforms on the Earth's surface can be broadly classified into three categories. Number one, landforms of first order or first order landforms. First order landforms. So these first order landforms are continents and oceans. So these first order landforms are continents and oceans. Then there are second order landforms. Second order landforms. These second order landforms are developed or formed after the development of the after the formation of the first order landforms. So these second order landforms are, you can say, these are the mountains. These are the mountains, and these are the plateaus, and some types of plains. Not all the plains, some types of plains are also second order development, which are formed due to some endogenic forces over these continents and oceans, and they given birth to these mountains, plateaus and plains. Then after this, there are some other landforms which are third order landforms. Third order landforms, and these third order landforms further subdivided into fluvial landforms, then Aeolian landforms, then fluvial Aeolian landforms, then glacial landforms, then karst landforms. So these are different types of landforms which are developed over this Earth's surface due to different mechanisms. If you discuss about all these three types of landforms, then this topic geomorphology will be over. Okay. Now we are going to discuss about the evolution of the continents and oceans. That means the evolution of the first order landforms. Now it is the evolution of continents and oceans. In previous class I explained you how this Earth as a planet evolved in the solar system, means from the same solar prominence. We have seen that there are these planets evolved at different points of time. That means, the sun evolved at around, the age of the sun is today 5 billion years. After the evolution of the sun, this Earth had been evolved from the sun at around 4.5 billion years ago. After that, this moon, the satellite of the Earth, had been evolved somewhere around 4.44 billion years ago. Likewise, after the formation of the sun, or from the sun Earth and from the Earth moon, there were different processes which took place inside the Earth. Means in the earlier stage, this Earth was like a molten gaseous material. At that time, this Earth was dominated by gases which are under very high temperature. That means in that stage, this Earth was in gaseous state. At that time, and later when this earth was in its gaseous state, that is somewhere around 4.5 billion years ago, later some meteoroids, asteroids, comets and other celestial objects, they collide with this earth. So these meteoroids, asteroids, comets and other celestial objects, they collide with this earth, and that is how when these elements comes and collide with this earth, they lead to form, or they convert it into the liquid state of, they lead to form the liquid state of the earth. That means now the composition, the material of the earth got transformed into molten mineral material, similarly molten metals, gases, dust and water vapor. Gases, dust and water vapor. So this is how the gaseous state of the earth gradually transformed into the liquid state. Now thereafter, now when this earth was in its liquid state, or the interior composition of the earth got transformed, changed into molten mineral material, molten metal material, molten gases, dust and water vapor. Now this entire liquid material which was inside this earth, which acts as a fluid, and this fluid tries to escape from the earth. Now because of which this molten material which erupted onto the surface through different processes, this molten material erupted onto the surface. So when this molten material erupted onto the surface, this is earth which is in molten state. Now this molten material erupted onto the surface, and this molten material gets deposited on their surface. Molten material gets deposited on their surface. So this is how up to now the earth, outer part of the earth is just like a plank. Now due to the deposition of this molten material from inside earth, so this molten material, which is basically made up of the rocky material, that is mineral content, and these minerals after reaching the earth, this is actually called magma. Inside it is magma, and this magma after reaching the earth, it got solidified, then it is called lava. So this is how the earth surface covered with this lava, it is solidified magma, and this is how for the first time a new sphere which is composed of the rocks or mineral material gets developed on this surface, and it is nothing but lithosphere. Lithosphere because it is composed of the liths. So that means inside magma, molten material reaches to that surface, and it finally led to the development of a sphere of rocks, that is lithosphere. Now what happened after the formation of the lithosphere? That means this lithosphere led to it had been developed over their surface somewhere around 3.8 billion years ago. Now after the formation of this lithosphere, what happened and how the present day continents and landform, continents and oceans came into being over that surface is subject part. Now this theory, which could able to explain the origin of the continents and oceans from this single lithosphere, that means by this time this earth was completely composed of the lithosphere, and the same earth after the formation of this lithosphere, this earth, what happened during this magmatic activity, apart from this molten material, there was also evaporation, there was also eruption of this water vapor and some gases. So when this water vapor and some gases also released onto the surface, and these gases cover on the surface led to form atmosphere. These gases cover. Similarly the water content over the surface, water content on this lithosphere, this is water content which is formed due to, because when the magmatic activity took place, Apart from the molten rock material, some gas also erupted, some water vapor erupted. This water vapor under condensation process is finally given birth to the rainfall, and because of which this entire lithosphere now it is covered with this rainfall. So this layer, which is composed of the water, that means it is the precipitation of the evaporation or water vapor present in the atmosphere, and this is led to the formation of a new sphere on this earth, and that is called hydrosphere. So that is how this earth in its gaseous, earlier it was in its gaseous state, later transformed into the liquid state, and finally it acquired the solid state, and by this time this earth got the lithosphere and atmosphere and hydrosphere. It is what happened on the periphery or exterior of that surface. But what happened in the internal structure? So in the internal area and the interior of the earth, when this material is in the molten state, when the magmatic activity took place, then the inside the earth, the material got concentrated according to the densities. That means the material gets deposited, or the material got concentrated in concentric circles. The material gets concentrated into concentric circles, and some material got deposited here, and some material gets deposited here, and some material gets deposited here. That means here it is the most dense material gets deposited at the center, and here the medium dense material gets deposited here, and here the light dense material gets deposited here. That means in the interior earth, the material gets concentrated into concentric circles, and this process is called as differentiation. This process is called as differentiation. That is how simultaneously in the interior earth 3 layers were coming to being, and these layers given birth to the layered structure inside the earth. But on the outer side, on the exterior of the earth, 3 new components were coming to being, that is lithosphere, hydrosphere and atmosphere. Right. So this is how this earth had been transformed from its gaseous state to the solid state, along with the lithosphere, hydrosphere and atmosphere. And inside the earth we have different layers of the earth, or we have concentric layers of the interior earth. Okay. So we will discuss later about the internal structure of the earth. First let me tell you how these continents and oceans were developed. Now this concept for the evolution of the continents and oceans on the earth's surface, the concept regarding this evolution of the continents and oceans was given by a German geographer. He proposed a theory called continental drift theory by Alfred Wegener. Alfred Wegener, a German geographer, he proposed this theory in 1912, and of course it is one of the most important theory. And here the Wegener made an excellent attempt to explain the origin of or the evolution of the continents and oceans on the earth's surface. How? Because the earlier earth or the primordial earth has one single rocky layer. So one single rocky layer, it is lithosphere. But today we have different continents and different oceans, and earlier it was having only one single rocky layer, and it was lithosphere, and this single rocky layer was now later covered with water bodies. Water. It is hydrosphere. So it was the earlier or primordial form of the earth, where there was single continent or single lithosphere and a single water body, that is hydrosphere. But later these different continents and these oceans were evolved from the single continent and single ocean, and this concept excellently explained by this continental drift theory given by the Alfred Wegener. So here in this picture you can see, or this person Wegener, he called the single continent or single lithosphere at around 350 million years ago. So he called the single lithosphere on this earth surface, or it is, you can say, the mega continent on the surface as Pangea. He called it as Pangea. Later he called the single water body or mega ocean as He called it as Panthalassa. Remember these words. So he called the single continent as Pangaea, Pangea, Pangaea, and the single water body or mega ocean as Panthalassa. Right? So that means that around 350 million years ago, these continents and oceans were combined together, and it was the Pangaea, the single landmass, without the present day continents and oceans. Single landmass. See here, it is Africa continent, and it's South America, the present South America, North American part, and East Antarctica part, and the peninsular India part here, and it is Australian part. So all these lands are seems to be one single landmass, Pangaea, and the remaining part here, these water bodies, the present day Pacific, the present day, this Atlantic, all are seems to be one single water body. That was Panthalassa. Then later, this Pangaea, at around 250 million years ago, this Pangaea was broken into different parts, and here the South America landmass got separated from the Africa landmass, and here the Arabian Peninsula got separated from the Africa landmass, and it is the peninsular India which got separated from the Africa, and it is Antarctica landmass got separated from the Africa, and it is Australia landmass got separated from the African landmass. Now these are the small land masses in southern part of the Antarctica. Now this is how the single landmass now broken into different pieces. Now these pieces later they later to develop to form the present day continents and oceans. Means when this landmass was broken into different pieces, and these pieces come into being as separate continents. Here it is Africa continent today, Africa continent over the African plate, and it is South America continent here, and it is North America continent, North America here. So it is North America, South America, Africa, and it is the Europe continent. Of course, Europe and Asia combined together, it is Eurasia continent. And here this portion later led to form the Africa, Australia. So this is how the continents gets divided into different parts, and here the new gaps were created among these continents, and these gaps were filled by the water, and these were given birth to the new oceans. So here it is Atlantic Ocean in between this Africa and Europe on the east side, North America and South America on the west side. So when this single land which was on the surface was broken into different parts, now these new lands, the new continents were came into being here, and here some gaps were created, and these gaps were filled by the water, and it given birth to the new oceans. So today here it is the location of the Atlantic Ocean, a part of the Panthalassa. Here on the eastern side and western side, it is some of the Pacific Ocean, East Pacific Ocean and West Pacific Ocean. And here some waters are gets collected. So these waters are Southern Ocean, you can say, and here these waters are Arctic Ocean. These are Arctic Ocean. And here later, when this peninsular Indian landmass moves towards north and finally attached here, and this peninsular Indian landmass below each, here there was formation of new ocean, that is given the name Indian Ocean. Indian Ocean. So this is how from the single continent, single water body, different continents and different oceans were came into being. So similarly here, some landmass which was sea here, which was the part of Australia. Today the Australia is located here. Today the Australia is located here, and this is the Australia landmass, Australia continent, and here it is Antarctica continent. So that means, so that is from single continent, these 7 continents and these 5 oceans, these 4 oceans like Arctic Ocean, Atlantic Ocean and the Indian Ocean and the Pacific Ocean were come into being, right? So this is what the evolution of the continents and oceans, and it was explained by the continental drift theory given by Alfred Wegener. Now, to what extent this theory is correct? But here Alfred Wegener made an excellent attempt to explain the origin, to explain the evolution of the continents and oceans, and it is true that these continents and oceans were evolved from single continent and single water body. But here the merits are, it is an excellent attempt to give the explanation of the origin of the continents and oceans. But the demerit is, here he could not give the proper force for the drifting of the continents. Proper force for drifting of continents. So the proper force behind the drifting of the continents, according to Wegener, he told the force behind, according to Wegener, the proper force behind the drifting of the continents was tidal force, or he also stated that it is rotation period of the earth, rotation period or rotation due to the earth rotation. So you know that earth is rotating around itself. So as per the Wegener, the tidal force, that means the gravitational force of the sun and the moon and the earth, and the rotation of the earth are the reasons behind the drifting of the continents. But it is wrong, because if it is the same force, or if it is the reason for the behind the drifting of the continents, today also there is rotation of the earth, today also there is the effect of the tidal force or gravitational force of the sun and the moon on the earth, but there is no breakup of these continents. That's why this tidal force and the rotation of the earth are very small forces. These are very, very small forces, and these small forces could not drift such a huge continents. Okay, that is one demerit of the continental drift theory. Otherwise, it made an excellent attempt to explain the origin of the continents and oceans. And here this Wegener also given some excellent evidences in support of his theory. Evidences, according to him, the evidences were number one, jigsaw fit of the continents. Jigsaw fit of the continents means, so when you see these pictures and try to join one continent with the another continent, for example, if you take up the South America today, if you take up the South America, and if you see that the South America is adjacent to the adjacent to the Africa, then it is South America continent here, and it is Africa continent. So these two continents seems to be, they are coexist together in the historical past. And here this Arabian Peninsula today, it seems to be coexist together to the Africa Peninsula, African part. So that means this part, this is called as jigsaw fit of the continents. And later he given one more evidence in support of his theory, that is the occurrence of or the presence of the fossils of marsupials. So these marsupials are the earlier form of kangaroos, and these fossils were found. These fossils are found, in the northern part of, in the southern part of South America. These fossils are found in the southern part of South America here, and these fossils are found in Africa continent, and these fossils are also found in southern part of India, and these files are found in somewhere in these parts of Australia. These parts of Australia. So this is how. So this Australia, Africa, India, southern part of India, and South America, all these are having the presence of the marsupials. So that means these all lands might have been coexist together in the historical past. So that is one more theory given by or evidence given by the Wisner. Next, and there is existence of the coal mines in the northern hemisphere belongs to the same area. So the existence of the coal mines or coal deposits, the existence of the coal deposits in northern hemisphere. So these coal deposits of same origin or same age, coal deposits of same age or exist in the northern hemisphere. For example, the Appalachian coal deposits in North America, Silesian coal deposits in Poland, and the Karaganda coal fields in Kazakhstan. These are all the coal deposits formed somewhere almost at the same time in the historical past. Then the fourth evidence is the gold deposits. Gold deposits along the west coast of Africa here. So today there are the presence of the gold deposits here. There is Gold Coast, but the same type of gold deposit veins of the gold deposits are exist along the the southern part of the South America, the east part of the South America. The east part of the South America continent, you can see the existence of the gold deposits in the Brazilian part here. So here you can see the existence of the gold deposits. This part. So this is how the origin is here, but their remnants are here. That means these two might be coexist together in the historical past. So in that way, Wisner given excellent evidences to explain this theory, but he could not explain the proper force behind the drifting of the continents. So even then, in overall, you can say this continent drift theory is an excellent theory to explain the origin of the continents and oceans. Clear? Later, to explain these continents and oceans, the origin of the continents and oceans, or to overcome the demerits of the continental drift theory, later one more person called Harry Hess proposed a theory, and this theory is said to be seafloor spreading theory. Seafloor spreading theory. Harry Hess proposed this theory, which is called as seafloor spreading theory. Later, but here the Harry Hess also could not able to explain the drifting of the continents properly, completely, but he could able to overcome to some extent the demerit of the continental drift theory. But later, one more theory, that is plate tectonic theory. Plate tectonic theory given by three geographers, Mackenzie, Parker and Morgan. Mackenzie, Parker and Morgan, these three people, Mackenzie, Parker and Morgan, these three people, they proposed this plate tectonic theory, and according to plate tectonic theory, they could able to explain, it is the most successful theory, and here they could able to explain the drifting of the continents. So that is how the demerits of the continental drift theory and seafloor spreading theory are overcome, and the present day continents and oceans were evolved, was also explained by this plate tectonic theory. Plate tectonic theory is very good attempt, and of course it could able to explain this, the origin of the continents and oceans, and later the different geophysical phenomena. We will see later. So that means that is the end of the origin of the continents and oceans. And here let us see what are the plates and what happened in the case of plate tectonics. I will come to later this plate tectonics, because it is the internal part of the earth, somewhere inside the earth, but these are the outermost part of the earth, that is the lithosphere. Now this lithosphere had been divided into different plates, so that's why these are the continental plates and oceanic plates. And when there is convergent and divergent and transform plate boundaries between the plates, they given both different types of landforms that led to the drifting of the continents. We will come to the plate tectonic theory later at the end of the chapter. So it is clear that the present day continents and oceans were evolved from the single continent called Pangaea, and the oceans were developed from single water body called Panthalassa. And the present Indian landmass, which was the earlier part of this this Gondwana landmass, because when this Pangaea got broken into two parts, the first part, this is the Gondwana divided into two parts. It was the Gondwana, it was the Laurasia, or it was Angara land, northern part, but southern part it is called as Gondwana land. Remember this point. That means this Laurasia, that means Pangaea now broken into, it was Pangaea, this had been broken into two parts. One is Angara land and Gondwana land. Later this Pangaea or this Angara land given birth to, or Angara land divided into the present day North America continent, Greenland and Eurasia, that means Europe plus Asia. So Angara land given birth to North America, Greenland, Eurasia, Europe plus Asia. And this Gondwana landmass, it the southern part, it given birth to South America, Africa, the southern part of Africa, and Australia, and Antarctica, and you can say the present day peninsular India. So this is how all these parts are derived from the Gondwana land, and the northern parts are derived from the Angara land or Laurasia. Remember here one point, that is here the peninsular India, today it is in the northern hemisphere, but by its origin, by its evolution, it belongs to Gondwana landmass. Clear? So with that, the continental drift theory and the evolution of the present day continents and oceans. Now in sum up, you can say the present day continents. Today we have 7 continents. So these continents by area, the largest continent is Asia, and the second largest continent is Africa, and the third largest continent is North America, and the fourth one is South America, fifth is Europe, sixth is Antarctica, and seventh is Australia. So these are the 7 continents by their area. Today we have these continents, and there are 4 oceans. According to drift theory, there are 4 oceans. In that, the largest ocean by area is Pacific Ocean, and the second largest ocean by area is Atlantic Ocean, and third largest ocean by area is Indian Ocean, and fourth one, the small ocean is Arctic Ocean. But in some books it is also mentioned Antarctic Ocean or Southern Ocean, but here this Antarctic Ocean, Southern Ocean is not a separate ocean. When these waters when these waters, after the formation of these continents and oceans, now here the waters of the India Ocean, the waters of the Atlantic Ocean, the waters of the Pacific Ocean, these are combined together, and these given birth to the combined together, and these were given birth to the present day these were given birth to the present day yeah. So when these waters of the Pacific Ocean, Indian Ocean and Atlantic Ocean gets collected over the northern part of the Antarctica, and it seems to be a new ocean, but it is not a new ocean, it is Antarctic Ocean, or it is also called a Southern Ocean. Southern Ocean. So this is how these 7 continents and 4 oceans are came into being. So with that, the development, the origin of the first order landforms is over. Now we'll move to the next topic, that is second order landforms. Second order landforms. So these second order landforms, I already mentioned you. The second order landforms are mountains, plateaus, and some types of plains. So these mountains, plateaus and some types of plains, and these second order landforms are actually derived due to, or the reason behind, the force behind the development of these second order landforms, the force behind the development of second order landforms is endogenic force. So these endogenic forces means those forces originate inside earth. So those forces originate inside earth, they given birth to these endogenic forces, and these endogenic forces led to form these these second order landforms, these mountains, plateaus and plains. That means majority of the second order landforms, some of the mountains, some of the plateaus and some of the plains are formed due to endogenic forces, and these endogenic forces are nothing but those forces which originated due to some force, some mechanism inside the earth. So to understand these endogenic forces, you have to know the internal structure of the earth. Now here some of the plateaus and some of the plains are also formed due to exogenic forces. That means the second order landforms are formed due to endogenic and exogenic forces, and these exogenic forces are those forces which originate outside the earth. Those forces which originate outside the earth, these are exogenic forces. So these exogenic forces which originate outside the earth are nothing but, you can say, the temperature due to the sun, or these exogenic forces are mainly due to the sun, and this sun is responsible for the temperature, which is an exogenic force. The sun is responsible for this rainfall, it is an exogenic force. The sun is responsible for atmospheric pressure, it is an exogenic force. So that is how these exogenic forces are due to the sun, but endogenic forces are due to the earth. So these endogenic forces are developed due to inside earth, but whereas the exogenic forces are originated developed due to the sun. These are like temperature, rainfall, pressure and other types of exogenic forces, right? Now when these exogenic and endogenic forces are acting on the earth's surface, so when these exogenic and endogenic forces, exogenic and endogenic forces acting on the surface, they resulted in the development of second order land forms. So this resulted in the development of second order landforms. Okay. Now first we are going to discuss about the endogenic forces, and to understand about the endogenic forces, to understand about these endogenic forces, To understand about the endogenic forces, first you have to know about the internal structure of the earth. Or these endogenic forces are nothing but, these are originate from inside earth, so these are nothing but seismicity or earthquakes. Earthquake or seismicity is an endogenic force. And after this, volcanicity or volcanism is an endogenic force. And after this, folding is an endogenic force. Faulting is an endogenic force. That means these earthquakes or seismicity, volcanism or volcanicity, folding and faulting, these are all the forces which originate from inside earth due to some internal mechanism. So to understand about these endogenic forces, we have to know about internal structure of the earth. That means to understand this development of the endogenic forces, we have to know about the internal structure of the earth. So internal structure of the earth, or it is the interior earth. Interior earth. Now I explained in the beginning, while this earth had been transforming from its gaseous state to solid state, and from its gaseous state it transformed into the liquid state, and it finally acquired this solid state. And in its solid state, it on the outside it led to the formation of the lithosphere and hydrosphere, and on the outer side atmosphere, lithosphere and hydrosphere. But inside the earth, what happened? I told you the material get concentrated into concentric circles according to the density, and here it led to formation of the most dense material here, and medium dense material here, and least dense material here, like this. So this is called differentiation process, I explained you. So this is what now I am going to discuss about this internal structure of this earth, which had been occurred somewhere around 3.8 billion years ago in the evolution process, the transformation of the earth from its solid, gaseous state to the liquid state, and further to the solid state. So this is what the internal structure. So now to understand this internal structure, you look at this picture. So this is interior earth or internal structure of the earth, simply. So in this picture, so this is the earth. So this is the earth. Now you know that this earth is in geoid shape, but I told you in the inside earth the material get concentrated in the form of concentric circles. Now it is the innermost part of this earth, and it is the innermost layer of the earth, and this innermost part is called as core, inner core. Now this core is again divided into two parts. It is inner core. It is inner core. Then above this inner core there is outer core. Then it is the mantle portion. It is the mantle portion, the second layer. Now within the mantle, the uppermost part of the mantle is covered by asthenosphere, and it is the outermost part called crust. Now you can see the same interior structure in this form, like this. So it is the uppermost part. So this is uppermost part, which is called crust, is crust, and this crust is again divided into two parts, like upper crust and it is lower crust, upper crust and lower crust, and this is the second layer. So today this upper crust is extended up to a depth of, upper crust and lower crust, that means the average depth of the crust is up to 30 to 35 to 40 kilometers. Then after this, the next layer is mantle, and it is upper mantle, and below which there is lower mantle. So this is entire the mantle portion. Mantle portion. It is the mantle portion here, and it is the crustal portion, upper crust and inner crust. And here later it is the third portion, which is called core, and this core is again divided into two parts, that is outer core and it is inner core, and it is mantle. Mantle is again divided into upper mantle and lower mantle. So that means this earth had been divided into, in the interior earth there are different layers, and these are like this. So it is crust portion, and below which is mantle, and below which is core. And this crust is again divided into two parts, mantle is divided into two parts, and core is divided into two parts. Now come to this, one more explanation about this, one more diagram which shows the internal structure of the earth. This is core, and it is the mantle portion and upper mantle, it is the structure of the sun. Means, now come to this part, in the internal structure of the earth. This is upper, this is crustal portion, crust, mantle and core. Now let me discuss about all these internal areas one by one clearly. First it is crust. So this crust is basically, the depth of the earth, the thickness of the crust is from earth surface to a depth of 35 to 40 kilometers thickness. Then this crust is made up of rocks, and that's why crust is part of the, it is called as lithosphere. It is composed of the rocks or liths. Next, this crust can be divided into two parts. This crust can be divided into two parts, like upper crust and it is lower crust, or it can be divided into continental crust and oceanic crust, like this, continental crust and oceanic crust. So this is the portion where the continents are lies, and this is the portion where the oceans are lies. So now on the earth surface you can see the continents and as well as the oceans. Now below the continent it is continental crust, and it is below the oceans. These are all the water. So it is the below the oceans, it is oceanic crust. That means you can divide this crust into continental crust and oceanic crust. Now this continental crust is dominated by silicon. This crust is dominated by silicon mineral, silicon and aluminum. It is dominated by silicon and aluminum. So it is called Cl layer. But whereas oceanic crust is dominated by silicon and magnesium, it is called Sima layer. Continental crust and oceanic crust. Silicon layer, continental crust is Cl layer and oceanic crust is Sima layer. Now if you look at this picture clearly, here from the earth surface, if you take up the depth of the continental crust and depth of the oceanic crust, this oceanic crust lies somewhere in between 35 to 40 kilometers, but continental crust exists from zero, from earth surface up to a depth of 25 to 30 kilometers. That means you can say the depth of the oceanic crust is greater than depth of continental crust. Continental crust. Depth of the oceanic crust is greater than depth of the continental crust. And you can see, or you can say, so when the continental crust is like this, and here it will be the oceanic crust. It will be the oceanic crust. That means if you take up the thickness of the continental crust is more than the thickness of the oceanic crust. Is it clear? So that means here thickness of continental crust is more than thickness of oceanic crust, OC. Thickness of continental crust is more than thickness of oceanic crust. That means the thickness of the continental crust is up to some 30 kilometers, but its thickness is some 5 to 8 kilometers. Right? Then one more difference between continental crust and oceanic crust is, as this continental crust is made up of silicon and aluminum, these are light minerals, that's why its density is less. Whereas the oceanic crust, which is made up of silicon and magnesium, which are denser or which are heavier than the silicon, aluminum, that's why the density of the oceanic crust is more than the density of the continental crust. So one more difference between the continental crust and oceanic crust is the density of oceanic crust. Density of oceanic crust is greater than density of continental crust. Okay. So that means the average density of the entire crust. If you take up the average density of the entire crust, and its average density is, it ranges up to 3.3. It is the average density of the crust is some 1.5. Average density of the ocean crust is 1.5 gram per centimeter cube. 1.5 gram per centimeter cube. But you can say the continental crust density is 1.1 gram per centimeter cube, or the oceanic crust density is up to 3.3 gram per centimeter cube. In overall, it is in between 1.8 or 1 or 2 gram per centimeter cube, like this. That makes the difference. So in overall, the average density of this crust is, you can say, it is in between 2.2 gram per centimeter cube. 2.2 gram per centimeter cube, right. Then coming to the next layer, next part of the internal structure of the earth, that is mantle. Here, this portion. Now this portion, mantle, after this crust, crust is over here, and this is the mantle portion in the inside earth, and this mantle, its thickness is around 2,900 kilometers. Thickness is around 2,900 kilometers. Now this mantle further divided into, the mantle can be divided into two parts. This mantle can be divided into two parts, like mantle can be divided into two parts, like upper mantle and a lower mantle. That means from this part up to a depth of 1600 kilometers, that is upper mantle, and here in the 1300 kilometers, it is lower mantle. Now upper mantle and lower mantle are separated. Now if you take up the upper mantle, this upper mantle is having a thickness of 1600 kilometers. This upper mantle having a thickness of 1600 kilometers, and these 1600 kilometers in the upper mantle, within the upper mantle, here the topmost part, here this thing, it is made up of rocks only. This is upper mantle. In that rock, in the topmost 100 kilometers is made up of rocks. Now after this rocky portion in the upper mantle, so this is upper mantle, it is 1600 kilometers, and in that the top 100 kilometers, this is made up of rocks, and below this rock layer, it is for a length of 200 kilometers. Here there is another layer, so which is asthenosphere. Remember, asthenosphere, and this asthenosphere is composed of magma, and in this asthenosphere the material is in the molten state, or the asthenosphere is in liquid state. Now below which, again, this is the portion which composed of different types of minerals. This is the upper mantle composed of different types of minerals. Now this asthenosphere, and above which is composed of the rocks, and I already told you here it is the crust portion, and this crust is also made up of the rocks. Crust is also made up of the rocks. That's why this entire portion which is made up of the rocks from the here to here, this entire portion which is made up of the rocks is called as lithosphere. That means we can understand from this diagram here, you can understand from this diagram here, it is asthenosphere. This is asthenosphere. This is asthenosphere, and above this asthenosphere it is made up of the rocks. Of course, it is upper part of the mantle, but crust is also made up of the rocks. This is also upper part of the mantle. But from this you can distinctively understand that this lithosphere lies over the asthenosphere. So today this is the lithosphere in overall, which is some entire crust and some part of the mantle, and this lithosphere floats on the asthenosphere. Lithosphere floats on the asthenosphere. So that is what actually happening, the structure of the interior earth. So that is what upper mantle. Then coming to the lower mantle, this lower mantle is in solid state, and which is made up of minerals like periclase, that is MgO, magnesium oxide, and these are somewhat heavy minerals, and the density of the lower mantle is more than the density of the upper mantle, and its thickness is 1300 kilometers, right. Then next, coming to the third portion of the interior earth, it is core. Now this core is of 3600 kilometers thickness. Core is of 3600 thickness, and this core is again divided into two parts, like upper core and outer core and inner core. So this outer core, remember, this outer core is in a liquid state and inner core is in a solid state, and this core is basically made up of heavy metals. Core is made up of heavy metals like nickel, ferrous, cobalt, and molybdenum, all these things. So as the core is made up of these heavy metals, this core is called as, or heavy metals here basically nickel and ferrous. That's why core is also called as knife layer or nif layer, and that's how the density of the core is very high. So the density of the core is up to 13.3 gram per centimeter cube, density of the core. So that means most dense material because of heavy metals here. But I told you the density of the crust is up to 2.2 gram per centimeter cube, and the density of the mantle is so this is the lower mantle and the upper mantle, and here the density of the mantle is up to 5.5 gram per centimeter cube. So that means medium dense material mantle is, but the core is heavy dense material. The density, see here, the density is 13.3 gram per centimeter cube. Okay, so this is how in the internal structure of the earth, the light dense material, that is the crust, which is of 2.2 gram per centimeter cube, is concentrated over this on the outer edge, and a medium dense material with 5.5 gram per centimeter cube is considered here, and most dense material which is of 13.3 gram per centimeter cube gets concentrated over here. So that is the internal structures like core, mantle and crust. So this is briefly the internal structure of the earth, and you may get questions in the examination about this internal structure and its particulars. So this is the interior earth is got differentiated into different layers based on the density of the material. Okay, if you understand this internal structure, then you can understand the plate tectonic theory, or the mechanism of the earthquakes and the mechanism of the volcanoes. Okay, now we are moving to the next topic, earthquakes. We are moving to the next topic, earthquakes. So these are the earthquakes. So earthquakes are, this word earthquake derived from a Greek word called seismos, and earthquakes are some endogenic forces, or the forces which derived from inside earth. See, as you know the internal structure of the earth or interior earth, we have seen the layered structure inside the earth like this, and of which we have seen that this outer core, this is outer core, this outer core is in liquid state, and here the molten metals are there. These molten metals which are in the molten state, they are revolving around this outer core. So when this molten metallic material revolving around this outer core, it produces currents. It produces some currents, and due to these currents, due to the flow of the magnetic material here, and it also produces the magnetic field, and this magnetic field due to outer core of the earth, this magnetic field due to the outer core of the earth is called as geomagnetism. This magnetic field due to the outer core of the earth is called as geomagnetism. So this geomagnetism is due to outer core of the earth because this outer core of the earth is in liquid state, or it is made up of the metals, but these metals are in their molten state. As this molten metallic material revolves, it creates currents, and because of the currents due to the electromagnetic induction, it also produces the magnetic field. So due to the flow of these currents, there is always a lot of disturbance in the inside earth, and this disturbance from inside earth, it is reaches to the earth surface. This internal disturbance in the outer core is reaches to the earth surface through these interior layers. So from this outer core, this internal disturbance is reaches to the outer core through these layers throughout all the directions. But sometimes here the asthenosphere, which is part of the mantle, this asthenosphere which is made up of magma or which is in the liquid state, this asthenosphere acts as elastic layer. This asthenosphere absorbs the internal disturbances which are coming from outside outer core. That means here the asthenosphere acts as shock absorber to the internal disturbances. That is how this asthenosphere sometimes undermines the internal disturbances, suppress the internal disturbance, and so that it may not lead to the earthquake activity. But sometimes when the internal disturbance is very, very high, where the asthenosphere cannot absorb or cannot prevent or cannot suppress this internal disturbance, then it may reaches up to the crust. It may reaches up to the crustal portion. So when the asthenosphere is not in a position to control, then it may come up to the crust. Then at that time there will be crustal disturbance. There will be crustal disturbance due to this vibrating energy, or it is a form of energy reaches to the earth crust. It creates vibration or disturbance to the crust, and that crustal disturbance is called as earthquake. So earthquake is nothing but it is the trembling or shaking of the earth crust. It is shaking or trembling of the earth crust. So earthquake is nothing but the shaking or trembling of the earth crust due to the internal disturbances. But sometimes, even though if there is no disturbance in the outer core or there is no internal disturbance, sometimes, because as this crust is made up of layers, as this crust is made up of liths or rocks, as this crust is made up of rocks or liths, here these rocky layers which are arranged like this, these rocky layers, that means this first rocky layer has its pressure on the second rocky layer, and the pressure of these two rocky layers will be there on the third rocky layer, and their pressure will be there on the next layer like this. That means there is impounded pressure on these rocky layers. Now whenever the pressure cannot be balanced by these rock layers, and these rocks are also having some elastic nature, but sometimes these rocks may not able to control this balance, or whenever there is some internal force coming like this and which attacks this rocky structure, that means at that time these rocky layers are tries to adjust themselves to the internal disturbance. So when there is internal disturbance, then these rock layers are tries to adjust to the internal disturbance. At that time there will be crustal disturbance like this, and this crustal disturbance is called as earthquake activity. So that is what, when the internal disturbance took place, this internal disturbance tries to disturb the crust, the rocky structure, and at that time these rocks, due to their elastic property, they tries to adjust to the internal disturbance, but that type of adjustment is called as, or the type of crustal disturbance is called as earthquake. Okay. Now coming to the structure of the earthquake structure. So whenever it is the earth surface and it is some place where the vibrating energy or some internal disturbance originates, so this place where this vibrating energy originates is called as focus or hypocenter. So it is the place where this vibrating energy or internal disturbance originates is called as focus. Now from this focus, this energy travels in all the directions toward the or onto their surface, in all the directions. So it is their surface, it originates, it reaches to all the areas. Now for the first time this internal disturbance reaches to a particular place which is perpendicular to the focus. So this place where this earthquake waves reaches for the first time is called as epicenter. So look at the picture here. So this is inside earth, and it is, this is crustal portion like this, crustal portion below which is mantle. Now somewhere in the crust, here some internal disturbance originates. Now it is a point called as focus. Now here onwards, this vibrating energy moving to all the directions, and finally it reaches to the earth crust. So that means here this energy is gradually moving and it is coming to the earth surface, and this reaches to this place for the first time. This vibrating energy reaches to this place for the first time, and because it is perpendicular to the focus, and that's how this place which is perpendicular to the focus is called as epicenter, and it is lies on the earth surface. Epicenter is always lies on their surface. Now these waves which are coming from the focus to that surface in different fashions, these focus from the focus to the epicenter in different ways or in the different propagations. So these are the waves which carry this vibrating energy from focus to the epicenter. These are called as earthquake waves. These are called as earthquake waves or seismic waves. seismic waves. Because I told you this word earthquake originates from a Greek word called seismos. That's why the study of earthquakes is called as seismology. The study of earthquake is called as seismology, and these waves which carry this earthquake energy from focus to the earth surface are called as seismic waves or earthquake waves. See here, look at this picture. Here also the earthquake originates here. This is the focus. From this focus, the energy distributed in the form of waves throughout this space, and that is how these are called seismic waves. Understood, right? So now these waves which carry this energy from earth surface, from the focus, these waves which carry this energy from focus to the epicenter, and thereafter from epicenter to the nearest seismograph station, are called as seismic waves or earthquake waves. So let me discuss about these earthquake waves. These earthquake waves can be broadly divided into two parts. One is body waves, second one surface waves. Body waves and surface waves. Now these body waves are those which are traveling inside the earth, that is from focus to earth surface. These are body waves. So these waves are travel inside the earth from focus up to the epicenter, not below the not on the surface, up to the epicenter. So these are called body waves, and these body waves are of two types. These are P waves and S waves. But on the surface, once these waves are reaches to the focus, see here, once these waves are reaches to the focus, these waves are reaches to the epicenter, from the focus to the epicenter, these waves are called body waves inside the earth. Now once they reaches to the epicenter, from its epicenter they moves in different directions on the surface to the nearest seismograph station. So these waves which are moved from epicenter to the nearest seismograph station are called as surface waves. So surface waves are those which are moved from epicenter to the nearest seismograph station. So these waves which moves from epicenter to the nearest seismograph station are called as surface waves. Clear? So now these surface waves are again two types. The surface waves are of two types. So number one, R waves or Rayleigh waves. Or second one, Q waves or love waves. So in that way, in overall, these earthquake waves are of four types. Like P, Q, R and P, S, R, L or Q waves. So P waves, S waves, R waves and L waves, and of these two are body waves and these two are surface waves. So let me discuss about these waves one by one. First coming to these P waves. Now P waves means primary waves. So the waves which started from the focus, which travels from the focus towards the epicenter. So these waves which originates from the focus and they are coming towards the epicenter for the first time like this. So these waves are called as primary waves. That means these P waves are first to start from the focus, and these P waves are fastest earthquake waves. So the velocity of the P waves is very high, and these average velocity is 8 kilometers per second. And these P waves can pass through liquids as well as solids, because inside Earth some parts there is liquid material, some part remaining part there is solid material. But these P waves, they can pass through either the liquid material or to the solid material. That's why P waves can pass through both solids and liquids. Pass through both solids and liquids. Then later these P waves can pass through both solids and liquids, and these are the fastest earthquake waves, and these P waves follows longitudinal wave propagation. These P waves follows a longitudinal wave propagation. So these P waves follows longitudinal wave propagation, means here the moment of the vibrating particle is parallel to the wave direction, is parallel to the direction of the wave. For example, it is the direction of the wave, and here the vibrating particles are also moves in the same direction of this wave. So this is when the movement of the vibrating particles is parallel to the direction of the wave. That means it is when the wave is moving like this, the vibrating particles are also moving like this. So this type of wave propagation is called as longitudinal wave propagation. So here the vibrating particles are also moves along with the wave direction. So it is called as longitudinal wave propagation, and it is shown by, our best example is sound waves. Sound waves in the air also follows the same propagation. Don't confuse here, sound waves are not P waves, but the propagation of the sound waves is also like the longitudinal waves. So this is how these P waves are passing from one place to another place, or from through the rock strata. When these P waves are passing through the rock strata like this, back and forth, front and back and forth, this type of propagation, that's how these P waves are called as push waves. These P waves are called as push waves, right? So then coming to the S waves, and these S waves are nothing but secondary waves. Means S waves starts after the arrival of the P waves. S wave starts from the focus after the arrival of the P waves. So these S waves are called as secondary waves because they starts after the beginning of the S waves, or these S waves reaches to the epicenter from the focus after the arrival of the P waves. Once P waves reaches to here, then S wave starts, and they will also reaches to the epicenter. That's how these are secondary waves, and these S waves are second fastest waves. These S waves are second fastest waves. And their average velocity is 6 kilometers per second. But remember, these S waves, they cannot pass through. These S waves cannot pass through liquids. Means these S waves can pass through solids only. That means wherever there is liquid material, these S waves cannot pass through that liquid material. For suppose S waves cannot pass through asthenosphere, S waves cannot pass through outer core because it is in solid state, right? Then these S waves follows transverse wave propagation. These follows transverse wave propagation. These S waves follows transverse wave propagation. You know, transverse wave propagation means it is opposite to the longitudinal wave propagation. When the wave is moving like this, and the vibrating particles moves in opposite direction. The vibrating particles moves in opposite direction to the wave propagation. The vibrating particles moves in opposite direction to the wave propagation, like this. Means here the vibrating particles are moves like up and down like this. Not in the case of P waves. P waves, the waves are moves like this, the vibrating particles. But in the case of S waves, the moves up and down. So this is how the propagation of the vibrating particles is perpendicular to the wave direction. This is called transverse wave propagation. So because of this, these S waves cause a lot of shear when they are passes through the rock strata. They cause a lot of shear like this, and that's why these S waves are called as shear waves. S waves are called as shear waves. SHEAR, shear waves. These S waves are called as shear waves. Okay, so these are S waves, which are also called as shear waves, and which cause a lot of crustal disturbance inside that because of their propagation. Okay, then coming to the surface waves, I told you the surface waves are of two types again. So these surface waves are those which originate or which starts from the epicenter to the nearest seismograph station. Now these surface waves are R waves, Q or L waves. Q waves or L waves, and these R waves follows longitudinal wave propagation. R waves or Rayleigh waves follows longitudinal wave propagation, whereas Q waves or L waves follows transverse wave propagation. So that's why these Q waves or L waves, when they are passing through, see here in the picture. So this is the propagation of the L waves or Q waves like this, to and fro. But this white color, it shows the propagation of the waves in the form of you can say in the form of longitudinal wave propagation. This white color here, it shows the R waves, but these waves which are up and down, which shows the Q waves. Now these Q waves, because of their propagation, or these love waves, because of their longitudinal propagation, these cause lot of destruction on their surface. That's why these love waves are more dangerous, or they cause more destruction. So Q are love waves which cause more destruction, right? So in overall, if you take up the body waves and surface waves, body and surface waves, here surface waves are destructive. Than body waves. And within the body waves, surface waves are destructive than body waves, and within the surface waves are, among all these earthquake waves, love waves are dangerous. Love or Q waves are destructive. Clear? So it is the important thing. Then coming to the types of earthquakes. So you know the meaning of epicenter and focus. Depends on the depth of the focus. These earthquakes are of three types. So it is the epicenter. It is the epicenter on that surface. Here, and it is focus somewhere here. So depends on the depth of the focus. These earthquakes are of three types. Number one, low focused earthquake. B, medium focused earthquake. 3, deep focused earthquake. Low focused earthquake, medium focused earthquake and deep focused earthquake. When the depth of the focus is up to, that means when the depth of the focus is 0 to 30 kilometers, when the depth of the focus is 0 to 60 kilometers, that is from earth surface up to a depth of 60 kilometers, it is called low focused earthquake. When the depth of the focus is 60 to 300 kilometers, the depth of the focus is 60 to 300 kilometers, which is called medium focused earthquake. Medium focused earthquake, 60 to 300 kilometers. So when the depth of the focus is more than 300 kilometers, the depth of the focus is more than 300 kilometers, then it is called deep focused earthquake. Deep focused earthquake. That means you can understand in very simple manner. So it is the epicenter, or it is the earth surface, and it is a low focused earthquake when the depth is up to 60 kilometers, and it is medium focused earthquake when the depth is up to 300 kilometers, and more than this it is a deep focused earthquake. Deep focused earthquake means, if you observe all these low focused, medium focused and deep focused earthquakes, of all these three types, remember, of all these three types, low focused earthquake, of all these three types, low focused earthquakes are more dangerous. Low focused earthquakes are more dangerous, and these low focused earthquakes are more destructive, because when the focus is nearer to the crust, when the focus is nearer to the crust, here it is the focus and it is the crust, then more amount of vibrating energy reaches to the crust, and when the more amount of energy reaches to the crust, which cause a lot of destruction. That is how low focused earthquakes are dangerous. Similarly, surface waves are dangerous or destructive, and within the surface waves, low or Q waves are dangerous and destructive. So this is about the earthquakes, and the next class we will see the magnitude of the earthquakes, like the intensity of the earthquake, the magnitude of the earthquake, the intensity of the earthquake, and the measurement of the earthquakes, and about these earthquake shadow zone and all these things, right? Okay, thank you.